Welcome back to Reconstructing Relativity. Today I'm going to take a break from the normal series and do a little sidebar discussion on the Michelson-Morley experiment. Next video I'll be back to building our constructive model with the third mode of energy motion that I've promised. So the Michelson-Morley experiment, one of the most famous scientific experiments ever done. Very important historically, very relevant to relativity, and so we're going to quickly review it, what it was, and then discuss the significance historically for relativity. Obviously, Michelson and Morley were the experimenters. It was done in Cleveland, Ohio in 1887, and it was an attempt to measure the speed of Earth passing through space. It failed. It was an epic failure. It did not measure that, but it had a huge impact on physics, and oftentimes when experiments don't go the way you expect them to, that's where you really learn the most. That's what happened here, sort of. The Michelson-Morley experiment really confounded constructive modeling at that time. They thought they had a handle on how things worked, but the idea of light as a wave through space just didn't seem to work out the way they thought it would. And in fact, it tended to support Einstein's formal principle that the speed of light will be measured to be the same by all observers regardless of their motion. And so this experiment is one of the reasons that Einstein went the way he did. He couldn't figure out the constructive model, went with a formal principle. The Michelson-Morley experiment was built on a metaphor very similar to the bug metaphor we used earlier. In this metaphor, a swimmer crosses a stream a certain distance d and comes back, and then the same swimmer swims upstream and then back down to the starting point. And the swimmer is assumed to always swim the same speed through the water. So in order to go straight across the river, the swimmer has to angle into the current a little bit in order to keep going straight across. But then upstream and downstream, the times are different. And if you compare the times on these two courses, assuming the equal distances and the same speed of the swimmer through the water, you come to the conclusion that you can, by comparing the times of these two courses, you can backwards compute what the velocity of the river is. And the difference in times between swimming across the river and upstream and back down is gamma times twice the distance over the speed of swimming. Exactly the same mathematics that we used in an earlier video when we talked about lateral bugs. Same idea, same exact idea. Michelson planned to actually use light as the swimmer to measure the speed of the river. In other words, the speed at which the light-bearing medium of space, which they then called the luminiferous ether, was rushing past the Earth. How fast was the Earth going through space? Measure how fast space is going past you. Here's a picture of Michelson's earlier interferometer, which is the name of the apparatus. This is from 1881. Before their famous experiment, but he had been working on this device. Essentially, there's a source of light from one of the short arms. It shines towards a semi-silvered mirror that's set at 45 degrees. So some of the light passes straight through that mirror, and some of it gets reflected at 90 degrees. So the light travels down these two arms, hits a regular mirror, comes back, goes through another semi-silvered mirror, which allows those two beams of light to recombine to form one beam of light again. By 1887, they used more mirrors to increase the path length for more precision. So you start with a light wave, and then you split it into two light waves of smaller amplitude, but they'll be in phase. Now, if the two beams of light traveled perpendicular paths, equal distance, and equal speed, ideally they'd come back perfectly aligned when they They'd form back together into one wave, be identical to the original wave. But if they took different times to go through two different paths, they wouldn't be perfectly aligned. In fact, you wouldn't know how misaligned they were. How could you tell the difference? There's no way to put a little mark on the waves like I've shown in this picture here. You just have waves come back and they add up together. And how do you know? How do you time? The time difference between the arrival of light is so small that they couldn't possibly catch it with a clock. Have to do something a little trickier than that. The trick, let the whole apparatus rotate. Then the slower path would become the faster path, and the resulting summation of waves would show that the waves were passing each other. As the returning waves pass each other, the recombined wave would sometimes cancel and sometimes constructively interfere. This was the interference pattern seen in their experiment. As the waves would pass each other, the fringes would move. All they had to do was count how many fringes moved during the rotation of the apparatus through 90 degrees. And then they'd be able to figure out the speed of the Earth moving through space. Or so they thought. The interference fringes should move as the apparatus turns. Rotation of the Earth might do it. Just wait a quarter day to turn 90 degrees. Watch those fringes for 6 hours. But the fringes never moved. Was the interferometer sensitive enough to measure speeds? What kind of speed did they expect to measure? Well, even the rotation of the Earth around its axis would give them 833 miles an hour, which was marginal, but even that should have been detected. But the speed of the Earth orbiting the Sun is a much higher speed than that. And combined with the Earth's rotation to give them the turning of the interferometer, they really should have expected a handful of fringes to shift. And my number might not be quite right. Somewhere around 5, somewhere in that ballpark. Definitely sensitive enough, even though it's a very small gamma. This is a very sensitive machine. Should have been able to detect it. But they got virtually no fringe shift. And I love this picture here. They put the entire interferometer on a huge sandstone block to isolate it from vibrations and temperature changes and everything else that could happen to it. Floated it in a pool of mercury so that they could smoothly rotate it in a matter of minutes through 90 degrees right there in the laboratory. And nope, still no. Watching the fringes the entire time, they got no fringe shift, none whatsoever. What could this null result mean? Nobody really knew. They talked about ether dragging. Are you kidding me? Or the Earth is dragging space around with it? No, that doesn't make any sense. Then this Dutch physicist named Hendrik Lorentz had a thought. He said that, well, if the upstream-downstream distance somehow gets smaller by ratio gamma, then the time difference of the two paths would always be zero. If moving through space somehow shortened the apparatus in the direction of motion through space, just by that amount, it would work out. You'd never be able to get any fringe shifts if that happened. Darn right, Lorentz. He was on the right track. But at that time, they couldn't see any reason why something would shorten in the direction of its motion through space. There was no awareness yet about wave nature of matter, no idea about mass being convertible into energy. And furthermore, Lorentz went on and did some more math and came to the conclusion that, yeah, if something's moving through space, it would have to slow down. There would have to be a change in its time rate also. And at that point, it was just like ridiculous. Like they couldn't see why that would happen. But Lorentz wrote out his equations involving length shortening and time slowing down. Einstein went another way. The Michelson-Morley and other experiments suggested to him that the speed of light was constant in all directions. That was another way to think about this experiment. Regardless of any measurer's motion, Einstein's formal principle of relativity, that's what Einstein took away from this failed experiment. The really funny part is that the result of Einstein's analysis was that he came to the same equations as Lorentz. But Lorentz wrote them first, and so Einstein's equations are still called the Lorentz transformation equations. Einstein discarded the entire notion of the luminiferous ether, the ether. Robert Laughlin, Stanford University, 2005. The modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic ether, but we do not call it that because it is taboo. Yeah. And this, I believe, is the real reason no one has put forward a constructive model. Don't want to get close to thinking about that. It's not a good idea. Because of the history behind it, this whole idea of trying to build a constructive model based on waves and space, it's just taboo. It's not a good idea if you want a career in physics, I suppose. But I don't have to worry about that. I just want to make relativity make sense. And I've done that for myself, and I want to do that for you. So we'll get back to it in the next video. Thanks for watching. Please like, subscribe, comment, share, all that good YouTube stuff. By the way, my book didn't cover Michelson-Morley with this much detail. It's just for YouTube. Now for a beautiful musical outro from Phil Oakes. See you next time.
The world spinning madly, it drifts in the dark, swings through a hollow of haze, a race around the stars, a journey through the universe ablaze with changes